The problem which I am going to be discussing is house robber. This problem statement says you are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected and it will automatically contact the police if two adjacent houses were broken into on the same night. Given an integer array nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. So, while I was solving this problem, I watched the YouTube video of this problem statement where it mentioned that Google really loves asking dynamic programming problems. So I'll make sure to practice more dynamic programming problems. Coming on to the problem, we start making different combinations and eventually we will get our maximum result. To solve such type of solution, it is better to solve a small segment first. At every house, we make one of the two choices, rob it, and then we must skip the previous house or skip it and take whatever best value you got up to the previous house. The solution code uses a space optimized DP approach by keeping track of only two values instead of a full DP array. Here, rob1 represents the best amount we could rob up to two houses ago, and rob2 represents the best amount up to the previous house. For each house n, the algorithm decides whether it's better to rob this house, which gives n plus rob1, or skip it, keeping rob2, and stores the better option in temp. Then it shifts the window forward. Rob1 becomes the old rob2, and then rob2 becomes the temp, reflecting the new best total so far. After processing all houses, rob2 holds the maximum money we can rob without hitting adjacent houses. The time complexity of this problem is big of n and space complexity is big of 1. The patterns which are observed while solving this problem statement are first one is pick or skip DP transition. Second is sliding window DP with big of 1 memory. Third is converting story constraints into array recurrence. Fourth is maximum non-adjacent sum pattern. Fifth is greedy versus DP decision making. Sixth is overwriting DP states to optimize space. Seventh is sequential DP where each index depends on the previous indices. Eighth one is linear scan optimization on arrays. Ninth is using two pointers variables to compress DP. 10th one is state machine DP, thinking two states, rob or skip.